Okay, so I'm going to show you how to do a Hardy-Weinberg problem. So I'm going to start with number 4 on the Hardy-Weinberg problems. This is the second set of Hardy-Weinberg problems. It's on Schoology. Oh, low battery. All right, so I'm going to read number 4. So it says a population's in Hardy-Weinberg equilibrium. It says 38% of the individuals are recessive homozygotes for a certain trait. And then it asks, in a population of 14,500, calculate the number of homozygous dominant individuals and heterozygous individuals. So I will tell you that this is one of the most common things about Hardy-Weinberg is that you will usually start with the homozygous recessive individuals. That's because if it shows you the dominant individuals, remember that both homozygous dominant and heterozygous show the dominant trait. So you don't know how many are homozygous dominant and how many are heterozygous, but if they tell you the homozygous recessive, you always know that that's the little letters, right? So it's almost always with Hardy-Weinberg, you'll start with that. So if it says that 38% of the individuals are recessive for that trait, all right, so remember that in Hardy-Weinberg, your Q squared is your homozygous recessive trait. So what I'm going to do is I'm going to say that 0.38, right, that's 38%, that's going to equal my Q squared. All right, so your Q squared is how many show the homozygous recessive trait. So right there from there, then I can figure out Q, because then Q would be the square root of that. So, all right, if you put that in your calculator, you would see that Q, the square root of 0.38, is 0.62. All right, so I know that Q is 0.62, and from then I can also figure out P. So P, remember, P plus Q equals 1. So if I subtract 1 minus 0.62, I would get P. So that would be 0.38. Okay, so Q and P equal 1 together. So if you subtract 1 from the other, from 1, you would get the other one. So once you find Q, it's easy to find P. All right, so now the problem asks for the number of homozygous dominant individuals. Well, homozygous dominant is P squared. Okay, so I know P here is 0.38. So all I have to do is do 0.38 and square that, and I get 0.14 if you put that in your calculator. All right, so P squared is, or my homozygous dominant individuals, the frequency is 0.14. Okay, so now it's asking, in a population of 14,500, calculate the number of homozygous dominant individuals. So all I'd have to do is take that times 14,500, right? So 14% of that. And when I do that, I get about 2,030 individuals. Okay, so that answers the first part of the question. Calculate the number of homozygous dominant individuals, 2,030, all right, out of the 14,500. And the second part of the question asks, how many are heterozygous? Well, my heterozygous is 2PQ. All right, so that's my heterozygous, the number or my frequency of heterozygous traits. All right, so P, just a reminder, P and Q are my alleles, and then the P squared, the Q squared, and the 2PQ are all the number of individuals. That's my homozygous dominant, heterozygous, and homozygous recessive. So 2PQ is my heterozygous, so I would take 2 times P, which was 0.38, and Q, which was 0.62, and if I multiply all that together, I get 0.47. So to figure out the number of individuals, I would have to take that times 14,500 again, and that turns out to be 6,815 individuals. All right, that show the heterozygous trait. Okay, so that answers those two questions. Okay, 2,030 individuals show the homozygous dominant trait, and 6,815 show the heterozygous traits. Okay, so I just did 4 because I wanted to show you an example of the problem. I think you should be able to do some other ones. I'm going to come back and show you the last question on this sheet here because it's a little more involved.